Welcome to the first part of Lecture 15, Line Integrals and the Gradient. The title of our talk is Path Independence, Curl-Free, and the Gradient. So we want to talk about path independence. Previously we saw if an integral between 2 points along some curve parameterized by S of the vector field F dotted into the tangent vector T, if that integral was independent of the path between P and Q, then we learned that the curl of F, or del cross F, was equal to 0. Now the converse is also true. If the curl vanishes for the vector field, then that integral will be path dependent, as long as that integral is in a region where the paths lie in something that's called simply connected, and that's detailed in the book. I have a picture for you here on the left-hand side that sort of shows the difference between something that is simply connected, something that is not. Essentially, something is not simply connected if it's got some holes in it, and if I can wrap around a curve around one of those holes and it gets caught on those holes, if I tighten it up, thinking in terms of things like topology, then the region isn't simply connected. And on the upper curve, we're just illustrating clearly this issue that if I'm integrating from point P to point Q and I have two different paths, C1 and C2, it doesn't matter. The integral ends up being the same. And as a sort of heuristic way of thinking about this, effectively what we are trying to say is that if that integral is a total derivative, then it only depends on the endpoints from the fundamental theorem of calculus. And so in situations where that function can be written as a total derivative, that f dot t, then you would expect there to be path independence. And what is intriguing is that the condition that requires us to be able to write it as a total derivative is simply that the curl is equal to 0. That is by no means obvious, but we're going to show you that that is actually the case. Okay, so what we're going to do is we're going to start from a slightly different scenario. We're going to look at vector fields that are the gradients of scalar functions, and so we're introducing this new operator called a gradient, which is d by dx times the unit vector in the x direction plus d by dy times the unit vector in the y direction plus d by dz times the unit vector in the k direction, or the z direction. And what that tells us is that the derivatives are somehow related, because not exactly related, but they're effectively derivatives of something that is a scalar function. So there's a relationship between derivatives of the vector field and the spatial components of the vector field, because the derivative in the x direction leads to the component in the x direction, and so forth. All right, we're now going to let S be the arc length parameterization of the path. I'm not sure that we really discussed what arc length parameterization is. We're going to go into this in great detail quite a bit later in the class. But effectively, if I have any path, I can calculate its arc length along the path. And I can then say if I've moved a certain distance along the path, I can find out what the arc length is for that distance. And I'm going to use that as a parameter to tell me what is the x, y, and z components of the path. And so I'm going to write those x, y, and z components as x of s plus y of s plus z of s multiplied by the corresponding unit vector. And when I write it in that sort of path arc length parameterization, which at the moment I have to only think of as being possible in theory, because actually carrying that out is quite painful to do for anything except a very simple path. But if I have that way of writing what the path is as a function of some parameter, then the tangent vector becomes the partial derivative of x with respect to s of I hat, plus the derivative of y with respect to s of j hat, plus the derivative of z with respect to s of k hat. And now, when we look at what is f and dot it into t, what you find is the z component, the x component of f is just df by dx, or d psi by dx, and I have to multiply that by dx by ds. And I have to add to that d psi by dy multiplied by dy by ds, plus d psi by dz multiplied by dz by ds. And the net effect of this is that that is exactly the same as the total derivative of psi with respect to s. Think of it again. Psi is a function of x, y, and z. X, y, and z are each functions of s. So the total derivative of psi with respect to s would be the partial derivative of psi with respect to x, multiplied by the derivative of x with respect to s, plus the partial derivative of psi with respect to y, multiplied by the derivative of y with respect to s, plus the partial derivative of psi with respect to z, multiplied by the derivative of z with respect to s. And so now what we've done is we've written f dot t as a total derivative. We're now going to integrate, and you can see the ds's cancel, if you like, and what we get is we get the difference of psi evaluated at point Q minus psi evaluated at point P, and that is clearly independent of the path. It doesn't matter what kind of path I take to go from one point to the other, because I'm integrating a total derivative. I just get the antiderivative evaluated at the endpoints, the difference between them. That just comes from the fundamental theorem of calculus. Okay, let's look into this idea a little bit more. If we start from some initial point, x0, y0, z0, and then define the function psi to be the integral from that initial point to some new point, x, y, z, of f dot t ds, and so we have a little sketch of a schematic of how this would work. We start at some point x0, y0, z0, and we end up at some point x, y, z, and we pick some path. Actually, it doesn't matter what path we pick because f dot t we know is a total derivative and it's independent of the path itself, just depends on the endpoints. So that makes this a well-defined function. And because it's a well-defined function, I can now start thinking of doing things with it, like taking its derivatives. So what we do to look at its derivatives is we look at some very special paths. So we assume we go from x0, y0, z0 to x0, yz. So we don't change the x component along the path c1, and then along the path c2, all we do is change the x component. And then if I want to take the derivative with respect to x, the x only appears in this path c2. And so I'll be taking the derivative with respect to x of the integral of f dot the tangent vector, which is the unit vector in the x direction. So that's going to be the fx component. And because the final point lies in the upper endpoint of the integrand of the integral, what's going to happen is when I take that derivative, I'm going to evaluate the integrand at that upper endpoint. So I'm going to get the x component of f in the x, y, z point. And so what we found is d psi by dx is equal to fx, the x component of the vector field f. And by drawing some similar paths in the y and in the z directions, we immediately find that d psi by dy is equal to the y component of f, and d psi by dz is equal to the z component of f. And what that tells us is that we can construct psi from the equation, the gradient of psi is equal to f. So if you tell me what f is, the gradient of psi is equal to f is some differential equation. I can solve that differential equation to determine what psi is. Okay, so if I've done that and I found now what psi is, the vector valued function has this integral which is independent of the path, and we understand now that we can construct f's that are independent of the path by making them the gradient of a scalar. And what we want to now show is that if f is the gradient of a scalar, then the curl vanishes. And so that then verifies all of the three results that we have. Path independence of the line integral is equivalent to the curl vanishing, is equivalent to the vector valued function being the gradient of some scalar function, modulo the fact that we have to worry about these simply connected regions when we look at the issue of just the curl vanishing. Okay, so that means we got to calculate some derivatives. The curl of f is a complicated expression. It's the unit vector in the x direction times dfz by dy minus dfy by dz, plus the unit vector in the y direction times dfx by dz minus dfz by dx, plus the unit vector in the z direction times dfy by dx minus dfx by dy. All right, that's a lot of terms to calculate, but we know what each of those f components are because they come from the gradient of psi. So we know that fz is d psi by dz, and we know fy is d psi by dy, and we know that fx is d psi by dx. So let's plug that in. And what we find is we get the second derivative of psi with respect to y and with respect to z minus the second derivative of psi with respect to z and with respect to y. That's the x component. And then there's similar second derivatives for the y and for the z components. And what you see is these are the mixed second derivatives. Well, one of the first things you learn in multivariable calculus is it doesn't matter which order you take a mixed second derivative, they're always the same for functions that are smooth. And so since all of those mixed derivatives are the same, each one of those terms in the parentheses is 0, and I get that the curl is equal to 0. And so that shows us that the curl vanishes under the situation where the function is written as the gradient of psi. And from a notational standpoint, if you look at the left-hand side, this sort of makes sense because it's del cross del of psi. That's kind of like taking the cross product of something that is parallel to the vector that I'm taking the cross product with respect to. And then that, of course, we expect to have 0 because I can't take the cross product of two vectors that are parallel. That's always equal to 0.